Good evening, everyone. My name is David Herbert, and I will be presenting on the use of game theory in engineering design for my ME 541 project number 2. First, we will be looking at an introduction of game theory in decision making in general, and I'm going to relate it to the career that I'm currently working in, which is the themed entertainment industry. First, we need to talk about the implementation of teams in an increasingly complex world. I believe it's important to understand the foundation of the challenges that are faced by teams in decision-making scenarios because we can narrow down the solutions that are needed in order to solve those problems. Some of the challenges that I identified were the unique needs or variables from different stakeholders. For example, one person might have certain goals, and another person have completely opposite goals that might be directly challenging the first set of goals. Um, Competitive advantage for existing companies. And what I mean by this is whether or not it's a company that's breaking into the market for the first time or a company that has been existing for many years, they have to have that competitive advantage in order to capture the market share from other companies and stay relevant and profitable. Aging infrastructure and updating of old methodologies. What I mean by this is that as we move towards the future and continue to innovate, we must make sure that we are updating our old beliefs and our old tools in order to continue to innovate and push forward into the future. The time to implement projects. This is really challenging, especially for industries that are fast paced and require decisions almost to the minute. Implementation of seemingly opposing disciplines. For this, especially in engineering, when you have projects that require many different disciplines working on one project, it's important to have to manage and ensure that all of them are working like cogs in a machine. Whereas if they aren't, it can easily cause the machine to break down when those gears are not meshing. I think a great example that, highlights some of the challenges that are faced in decision-making scenarios is the themed entertainment industry, which is where I'm currently working at and where I would like to work in the future. For example, you have many different engineers working on building a roller coaster. You could have a structural engineer working on the foundations. You could have a civil engineer working on the infrastructure to support the roller coaster. You could have an architect who is making sure that the items being used on the project are up to specifications. You could have an electrical engineer who is wiring the control system for the roller coaster. Or you could have a mechanical engineer who's working on the roller coaster itself to make sure that it's safe for all of the guests that visit. But the thing that really ties it all together is that all of these people must work together as one unit, you could say, in order to develop and build and test and implement the project so that way it meets the goals for everyone. Circling back to this idea of competitive advantages within companies, I really thought that this definition by Air Focus of competitive advantage really captured the essence of it. Essentially, their definition is that competitive advantage is what makes a customer choose your business over another one. By understanding and promoting a competitive advantage, companies can win a greater amount of market share. But this concept extends beyond companies. It includes design teams, as they are competing, quote unquote, for time and money from sponsors. This idea of competitive advantage directly correlates to the idea of game theory and the implementation of collaborative and competitive teams. Game theory is when players attempt to maximize the benefit or utility they receive from a situation based on the choices of other players. Competitive advantage is very similar in the sense that it's teams trying to figure out what they bring to the table in order to maximize their benefit or, for example, money that they receive from a sponsor or notoriety that they might receive as well based on the environment that they are currently in. Overall, there are two different variations of game theory: cooperative and non-cooperative games. For cooperative, this is when decision makers are working together to maximize their benefit. Whereas non-cooperative, the decision makers might not be working together, or in some cases, might be trying to work against each other. Next, we'll examine one of the most famous examples of game theory to understand some of the concepts a little bit better, and that is the Nash solution with the prisoner's dilemma. In prisoner's dilemma, there are two players, quote unquote, within this situation. You have prisoner A and prisoner B. Both prisoners are presented with the following options: to confess or to remain silent. The number of years that they serve in jail is dependent on whether they both confess, both remain silent, or choose one of the other options. However, the interesting note here is that neither prisoner knows what the other player will do. Let's start with prisoner B. If prisoner A decides to confess, what is the better option for prisoner B? Well, obviously it's to choose to confess, because he'll only get 5 years instead of 20 years. Now, let's do the opposite with remaining silent for prisoner A. What should prisoner B do in this situation? He should also confess, because he'll get 0 years instead of 1 year. Now, if we go and swap to prisoner A, what should he do when prisoner B decides to remain silent? Well, he should choose to confess, because he'll get 0 years, whereas the prisoner B will get 20 years. Now, if prisoner B decides to confess, what should prisoner A do? Well, he should confess as well, because he'll get 5 years instead of 20 years. What's found is that the solution to this game is that they should both confess. This is called the Nash equilibrium point for this game. However, the interesting note here is that if the prisoners had just cooperated with each other, they could have both remained silent and only gotten 1 year. Whereas if the Nash equilibrium was that they both confess and they both got 5 years. Now that we've looked at the fundamentals of game theory and understand that it is a game in which two players are making choices that impact each other, and it could be cooperative or non-cooperative, we're now going to look at the articles that I examined for this presentation and the project in general. Within each article, the authors noted a different methodology in order to implement game theory into these decision-making environments. For the first article, it was titled "A Method for Interactive Decision-Making in Collaborative Engineering Design." This article overall talks about the idea that very little time is truly spent on the negotiation process for decision makers. The problem is that ideas from key stakeholders may not be truly implemented into the final design because they tend to see that humans don't like to reject the thinking of the group and don't like to counter what is being said. So someone might just go along with what the group says and not actually voice their true opinions. Products, services, or the overall concept is more likely to succeed when the ideas are implemented from many different stakeholders. To that end, the solution that was presented in the article is that there's an 8-step method that was a blending of a model for interdependent decisions and then an analytical coordination mechanism that kind of tied everything together. So the first part of the model is this idea of compromise decision support problems, or DSPs. This is the representation of the interdependent decisions that are made within a decision situation. It's implemented through the idea of a deviation function, and the mathematical idea can be seen below. But the main concept of the deviation function is the difference between what can be achieved and what is the actual goal of the decision maker. Preferably, this difference would be 0 because you'd be achieving what you set out to achieve or what your goals actually are. However, many times this is not the case. The second part of the method is this coordination mechanism for the previously discussed DSPs. and that is game theory. It's implemented through best reply correspondence, or BRCs, and it represents the strategy of the decision maker, what one player would respond with based on the choices of another player. As can be seen on the slide, there are four steps to develop the BRCs, and that's to identify other players' relevant variables, to do a design experiment or to set up a simulation of what would occur, to solve the compromised DSP with the deviation function, and then to fit a response surface, or basically all of the responses that could occur based on for the one player, the decision maker, based on the decisions or choices of another player. Overall, the 8 steps for the model can be seen below. First is to define the goals and identify any shared variables between the designers. This was previously discussed with the BRCs. Designers agree on 5 desirability levels for each of the goals, basically setting weights for how they would determine what is acceptable for the project. The standard deviation function is formed, and the weights are calculated based on those desirability levels. Minimization occurs for each designer's portion of the system, of the deviation function. Essentially, this allows for it to be taken into chunks and allows for a amalgamation of all of the designers sort of what they have control over within the design scenario. Each designer formulates a compromised DSP, which was previously discussed on the other slide. Using the DSP, each designer develops the BRC based on previously discussed methods, including the formulation of a response surface. Then the leader uses those BRCs to find values of shared variables that minimize the objective function. So the leader needs to be able to put together everything and develop this group objective function, and it becomes an optimization problem at that point. Once that optimization problem is solved, then the leader provides the values of the shared variables back to each designer, and then they can determine what their sort of unique variables are within their situation. Because there is a interconnection between a lot of the variables. For instance, the length of a rod might affect the torque that has to be applied to it. All the method has several pros and cons that are very important to understand. The main pro that I found with this method was is that it presented a systems perspective, a holistic approach to the overall design situation, and really allowed for the ideas to be decomposed for different decision makers depending on what is the decision that's being made. Whether that needs to be a structural engineer and a mechanical engineer, or adding in an electrical engineer, each person can have a section of the objective function that allows for their preference structure to be represented. It satisfies some of the tenets of Ayer's theorem, including unrestricted domain, Pareto principle, and individual sovereignty. However, some of the cons is that it violates two of the tenets of Ayer's theorem, so that essentially means that the group amalgamation for the objective function can only be said to be an approximation rather than a true description of the group. And there are approximations for the BRCs, because the problem is that the BRCs are dependent on a large amount of data and a large amount of information being fed that is not always possible under a given circumstance. And finally, it requires extensive coordination with that leader to give information back to the designers and then decide what the variables are. The next article that will be reviewed is a strategic decision-making architecture toward hybrid teams for dynamic competitive problems. The overview of this article is that of adaptive decision making for solving dynamic competitive problems. And this article really focused on that idea of competitiveness over some of the other methods that were described in the other two articles. It's truly a combination of sequence learning, model predictive behavior, and then finally game theory. There are two sort of sections within this method. The first one is modeling, and then decision making. Each section will be discussed further. Within modeling, you have empirical gameplay data and bi-level problem representation. For empirical gameplay data, this is really the idea of big data, or information that can be fed to computers that looks at past strategies to inform on what can be done in the present and what can be done in the future. However, this requires a lot of computing power and a lot of information being fed to the computers. Bi-level problem representation is really the idea of partitioning, or decomposing state space and variable space into different representations based on the interconnection between them. This can be done through manual partitioning, which is really just looking at the ideas and formulating them based on words alone, unsupervised partitioning, and supervised partitioning. These are primarily done through the use of computers, and it's done through looking at the feeding information and looking at the reward functions for each decision maker and breaking down the problem from there. Strategy clustering is the idea of variable states of the decision maker that represent the actions they would take based on internal and external factors. These are directly comparable to the previously discussed BRCs from the first article. For problem modeling, these are the models to represent system dynamics and the reward functions of the decision makers. This is done through a state space representation of both state variables and action variables to show what the next state would be based on the current state and the actions that the decision maker takes right now. Into the idea of decision making, there were two sections that the article focused on, and that was opening strategies and then differential game-based strategies. For opening strategies, this is the current state space information that is presented to the computer, and then the closest strategy cluster based on this information and the goals of the decision maker are presented, and then the decision maker can choose from those options what best to do based on what another player might do. And what's interesting is that the opening strategies can have varying time intervals for which they can be implemented. It could be a very short time period or a long period. It's really up to the decision maker to formulate the strategic goals that they have for the situation. For differential game-based strategies, these are the actions after the opening strategies. It's an optimization problem to minimize the previously discussed deviation function between the future state and the current state plus the current actions. Similarly to the other methods, it's important to analyze this current method to see the pros and cons. One of the biggest pros that I saw was that it's a comprehensive strategy compiled from historical data. You're really getting all of the previous information to inform the decision maker on what should be done in the present and could be done in the future. The strategy generation can be customized to different time periods, as previously discussed. Whether or not the person wants to stay in an opening strategy for a short period of time or a long period of time and then move into the differential game, it's really customizable and up to the decision maker. Similarly to the first method, there's a good amount of partitioning that can be done that allows the decision maker to branch out and sort of dissect the problem into sub-problems to focus one at a time on what needs to be solved. The cons are it's a winner-take-all approach. You're not having as much collaboration rather than the competitiveness that has been discussed. And there's a lot of computation time based on this comprehensive strategy that is a pro of the analysis of, or I'm sorry, of the method. And game theoretic decisions in this method yield a conservative value for the winner as compared to the loser within a certain time interval. This means that the computer favors choosing options that yield a lower reward due to the competition faced as a rational choice. However, as noted by the article, decision makers are not always rational, and they'll pursue actions that they perceive to yield the highest value. The third article that was analyzed was bi and multi-level game theoretic approaches in mechanical design. Within the article, the main concept that was discussed was the different variations on game theory. For cooperative games, you have Pareto solutions. For non-cooperative, you had conservative solution, Nash solution, and Stackelberg solution. The model was really aimed at approximating rational reaction sets, which are directly comparable to the BRCs and strategy clusters that were discussed in Articles 1 and 2 respectively. It was noted that current methodologies employ design of experiments, basically setting up simulations to determine variables and strategies based on previous information, through the idea of this response surface methodology, or RMSs, to determine the RRS for the decision maker. The holistic view of the model was centered on the idea of obtaining sensitivity information for the decision maker. First, an optimization problem with inequality and equality constraints was proposed. Derivations of the Kuhn-Tucker necessary conditions yielded the following equation. This shows that the strategy should be equal to the optimum value of the optimization problem, plus variation of this optimum value with respect to the parameters of the problem, multiplied by the respective change in those parameter values. The article presented solutions and methodologies for both a Nash and Stackelberg solutions. The first one that we'll discuss is the Nash solution. The Nash solution expands the idea discussed within the conservative solution, but does not restrict the player to purely seek solutions in which the least beneficial solution for their opponent at the expense of their own benefit. Therefore, the article pointed out that it can be difficult to determine the Nash solution due to it being within a non-linear point of reference. The first step of the method is to assume values for the strategies of both players. From there, solve the optimization problems to determine the optimum solutions for both players with respect to the original assumed values of the strategies. Next, use the methodology to find the sensitivity information for both players. Using this information, the optimum solutions can be linearized based on the previously discussed equation. Solving the system of linear equations yields optimum values for both players. If the difference between these optimum values and the assumed values divided by the assumed values is less than or equal to a certain threshold, then the values have converged to the Nash solution. The Stackelberg solution continues the expansion of the non-cooperative game by giving the different players roles within the game. Player 1 is determined to be the leader, while Player 2 is the follower. The idea is for Player 1 to dominate Player 2. This is due to the fact that Player 1 knows the optimum strategies of Player 2 and is basically able to predict the decisions that are going to be made. This allows for Player 1 to adjust their own strategy to find the scenario of optimal benefit. This methodology is very similar to what was presented for the Nash solution. The first step is to assume values for the leader. From there, solve the optimization problem for the follower based on the assumed value of the leader. Use the methodology to find the sensitivity information for the follower with respect to the leader. Using this information, the optimum solution for the follower can be linearized. Apply this equation to the leader's optimization problem and solve for the optimum values. If the difference between the optimum leader's value and the assumed leader's value divided by the assumed leader's value is less than or equal to a certain threshold, then the optimum values for both the leader and the follower are Stackelberg solutions. Now it's important to analyze the method to see what the pros and cons are. The first pro that was observed was that it allows for different types of game theory applications. The article presented on Nash and Stackelberg solutions, but as noted in the article, it can be extended to other scenarios with future work. It approximates the responses of the decision maker within the state spaces and requires fundamentally less computing power compared to the methods in the other articles. Some of the cons, though, are that it is more theoretical methodologies over data-driven methodologies. So it really requires a understanding of the theoretical concepts and knowing linear equations and methodologies to really drive the solution. After analyzing all of the methods within the articles, it's important to truly understand how they can be implemented within the real world. And I thought the best way to do that was to come full circle and view how they can be put into competitive and collaborative decision environments through the lens of the themed entertainment industry. As previously mentioned, I'm currently working within the themed entertainment industry and would like to implement new ideas and methodologies in the future to truly make decisions effective and efficient in the way that it is being implemented. Now, after analyzing all of the methods, I truly feel like the best approach was presented in Article 3, with the idea of using sensitivity information to approximate the response surfaces. Now, some of the reasonings for this and the benefits that I feel that this was the best method was that it requires less computational energy and time. As I have noticed through my career so far, a lot of the decisions are fast paced and require an answer in a short amount of time. When you have a lot of computations and having to wait on simulations to run, that eats up a lot of time that you do not have. Now, the second one is that it requires less historical data compared to other methods. With the themed entertainment industry, there's not a lot of data that is out there looking at some of the trends or, that could be used for decisions. And using less of that historical data and allowing the decision maker to make decisions is vital. Implementing fast-paced decisions, as previously discussed, the themed entertainment industry is very fast-paced and requires, responses sometimes within minutes. And then finally, adaptation to various scenarios. You're going to have a lot of different stakeholders and situations in which there needs to be a method that is adaptable to what is being the information that's presented and the variables within it. And I truly thought that Article 3 allowed that flexibility for the decision maker. I truly appreciate all the time that you have spent looking over my presentation and listening to me talk about game theory. As you can tell, I'm very passionate about this idea, and I really think that through my future career, I can implement the methods that I've learned through this project and help to implement collaborative and competitive team environments that truly push forward with innovation and new ideas. On this slide, you can see all of the articles and other sources that I used for this presentation. Thank you so much again.